Okay, we're looking at this thing that says examples of the divergence theorem in action. It says we confirm the conclusion of the divergence theorem by calculating both sides and getting the same answer. The region we want to use is a region from a previous problem, and it says h of xy equals 4 minus x squared, but just the part that lies above the xy plane. Only go as far right as 3, and they give us a vector field of zi plus xj plus yk. So what we're going to do is we're going to come over here, and we're going to see that this is actually a big problem, because if I'm going to do this by basically brute force, I need to find the flux out of each of those 4 regions. And so what I'm going to do is just set each up. I have a surface top, a surface right, a surface left, and a surface bottom. We'll do the most natural one first, which is the top. And remember, what we're having to do is we're having to calculate f dot dA and then set up the integral. Well, remember the equation here, so we're doing the surface top. We're going to have to do these one at a time and then erase, but here we go. So the surface top, on an integral, it's going to be a double integral, surface top, f dot dA, and we'll just start writing stuff in. Let's see here, I know that z equals 4 minus x squared, like that. All right, so here we go. They told us what f was. That's just z, x, y. Since we have a function of the form z equals, we know what the area vector looks like. It's supposed to be minus fx, so that's going to be 2x, minus fy, which is 0. And then the z, the k component there is going to be 1. We know we're going to get dx dy. So what we're still getting a double integral. I'm sitting on the surface. I now dot product those two. I'm going to get 2xz plus y dx dy. I might have to get rid of z because the only variables I can have are x and y. So we're going to do this. Going to take off the st because we're only leaving x and y now. Let's see here. dx dy, close enough. What I'm going to have here is 2 times x times z, which is 4 minus x squared, plus y, yay. And now I have to look at the region of integration, but I can look over here and see that the region of integration is just the region where x goes from minus 2 to 2, and y goes from 0 to 3, because it's just the smushed down surface, which just gives me that rectangle. So x goes from minus 2 to 2, y goes from 0 to 3, and we get a perfectly normal integral that finds the flux out the top, but that's all it does. It finds the flux out the top. Let's find the flux out the bottom. Okay, here. With the flux out the bottom, z isn't 4 minus x squared anymore. It's just z equals 0. So that's not so bad. I should be getting a double integral here. This is going to be out the bottom. And again, we're going to get f, so that's z, x, y. And I'm supposed to, using z equals 0 as our function, find the partial derivative. So partial derivative with respect to x is 0. Partial derivative with respect to y, even negative, is 0. And what I'm going to be left with is 1. I know this is going to be dx dy, like this. Oh, I do have to be careful, because the vector sticking out the bottom actually has a negative z component. So I'm going to get negative y. This is going to be dx dy. And this is what we get when we smush our region to the xy plane, but that's the same region as we had before. X goes from minus 2 to 2, y goes from 0 to 3, and we've at least set up a nice easy integral to do that finds the flux out the bottom. Let's find the flux out the left. A flux out the left is going to be a double integral where the surface is the left-hand side. We're still going to have f dot dA. Right? We know how to start. You always start with the f, which hasn't changed. We're still just finding flux of the same vector field. But now I need an area vector. Well, okay, the equation of the left-hand side is not s equals 0. It's not z equals 0. It is y equals 0. And that's now writing y as a function of x and z, and we know what the area vector is going to look like. It's going to be minus fx, which is 0. It's pointing out the left, so the y component is -1, or the j component is -1, and then the partial of that with respect to z again is 0. The variables are going to be dx dz, because y is a function of x and z there. So we're going to get an integral that looks like this. We're going to get minus x dx dz, and we have to worry about the limits of integration. Well, we're sitting here over in the xz plane. We have z over there is z equals 4 minus x squared. We slice like that. It enters when z is 0. It leaves at z equals 4 minus x squared. So this is going to go from 0 to 4 minus x squared. And then the chops for x we've seen go from as far left as -2, as far right as 2. So that's going to be the flux out the left-hand side. And okay, the total flux would require us to calculate one more thing. I want the flux out the right-hand side. So I'm going to go like this. Now you might be thinking, why don't we just use the shortcut? There are times when the integral we get for the divergence theorem we can't do. And if we could do little pieces, we're stuck doing the little pieces. So this is the surface out the right-hand side. I know I'm always supposed to take f, and that's just going to be z, x, y here. And now I want to write this, the area vector. Well, our equation isn't y equals 0 anymore. They told it was y equals 3, like that. Now I'm writing y as a function of x and z, so I know what goes here is the partial derivative of that with respect to x negatived, that's 0. I know this is going to be 1 because I have a area vector that's now pointing in the positive k direction. And then I look back at this and I want minus the partial with respect to z, well that's 0 again. The variables are going to be dx, dz, just as they were before. We can take this dot product without killing ourselves, and we're going to get x, dx, dz. The region is going to be what happens when we take that side and flatten it against the xz plane. And so we're going to have exactly the same limits of integration that we had before. X goes from, no, I want to do dz dx. Z is going to go from 0 to 4 minus x squared. X is going to go from -2 to 2. And we've at least, I think, set up the 4 integrals we would have to do in order to calculate the flux out of this region using surface integrals. In other words, the left-hand side of the divergence theorem. Now let's worry about the right-hand side. Right-hand side says, hey, you don't have to worry about f dot dA, which is great. We do have to calculate the divergence. We have a formula that's not that hard to remember, but let's get used to the new notation. We want to take the del operator and dot it with f. Remember that the del operator has the partial with respect to x, the partial with respect to y, the partial with respect to z, and I'm supposed to dot that with f, which is just z, and then x, and then y. Now, we're not really dotting, we're just putting this next to this, this next to this, this next to this. So we're going to get the partial derivative with respect to x of z plus the partial derivative with respect to y of x plus the partial derivative with respect to z of y equals 0 plus 0 plus 0. So the divergence here is 0, which by the way means at every point there is no divergence. Nothing's coming out of any box or any sphere I put around any of those points. But meanwhile, the triple integral is going to wind up being triple integral. We have a volume, we have 0. Now I suppose we could take the time and write out the limits of integration, but the integral should just be 0. And I like doing it that way a whole lot better.